In this video, we'll be talking about basic neuronal circuitry. So say suppose this is the membrane and there is this existing transmembrane potential which is Vm. For a particular ion, say suppose the membrane offers a particular resistance. So if you compare a biological membrane to an electrical circuit, we can assume that ion channels are equivalent to conductors with conductance G and a resistance which is inverse of the conductance, so R. The resulting conductance for all the potassium channels is Gk+. As a result of the normal electrical gradient, the electrical field and the force is in this direction. So according to the force acting on the particular ion, the current that develops only because of that is in this direction and it is equivalent to Gk plus Vm. However, in reality, we have another factor which is influencing this current flow, which is the normal existing gradient of the ion across the membrane. So, since the normal gradient of potassium is outside the cell, we can compare this to an electrical model in which there is a battery with the current flowing in the opposite direction. Say suppose this is I2 is minus Gk plus. So if we take a sum total of these two currents, which is still not the actual current which is flowing through the cell, we have Ix equals to I1 plus I2. So we get Gk plus Vm minus epsilon. This membrane is actually equivalent to a capacitor. So what is a capacitor? Capacitor is a device that stores charge between two conducting plates and there is insulating material in between. Can be a dielectric, or in this case these are the hydrophobic tails of the lipid molecules. So we can say that the membrane is a capacitor with a certain capacitance C. So it stores a certain amount of charge which we can derive from the current that is flowing through the capacitor. So say suppose the current flowing through the capacitor is IC is a function of the transmembrane potential. So IC equals to C dVm dt. So from here we can find out the value of Vm at any particular time. Tau is the time constant. So this factor is delta Q, or the charge that we talked about, which is stored inside the capacitor. So we can see that this is equal to V0 plus delta V, and delta V equals to delta Q by C. So if you have to summarize the entirety of this into a single circuit, it will look something like this. This is the capacitor or the membrane. It is connected in series with the cell, which is equivalent to the gradient, the concentration gradient for each individual atom. Say suppose maybe for sodium atom, for potassium atom, and so on. For potassium, sodium, it will be reverse total current which is flowing, and this is the transmembrane potential. This is the capacitor. This is E potassium, this is E sodium, etc. This is G sodium, G potassium, G chlorine. So the total current is actually a sum of the currents through the pumps, the currents through the individual leaky channels for the ions, and current through the capacitor. So Ix, this is the current through the leaky channels. We can also derive another important conclusion, that at rest the net flux throughout the entire circuit it is zero. So you can say Ix, sum of Ix equals to 0. And from here we come to a conclusion that the membrane potential, which is actually the RMP in this case, in per equation this factor will be constant and these are the changing variables. Okay, so if you say Ix equals to 0 and if you calculate it from there, Vm comes to be something like this. divided by the resistances. However, as we know from the last video, that all these channels do not equally contribute, all these ions do not equally contribute to the resting membrane potential. Potassium contributes far more to the resting membrane potential than sodium or any other ion, because the membrane is almost 100 times more to potassium than it is to sodium or any other ion, because of the various selectivity factors and presence of large number of potassium channels. That is basically what Goldman said. Fusible ions contribute to resting membrane potential, but not in equal proportion. They contribute to the resting membrane potential based on their charge, their polarity, and their concentration gradient, as well as the membrane's permeability towards these ions. Thank you.